Thank you, and thank you for the invitation to present this talk. So I'm Bianca Giaccone from Fermi, and I will present you Mago 1.0 and other SQMS activities. So let me first start with a quick introduction. SQMS is one of the five National Quantum Information Center that was established by the Department of Energy of the United States in 2020. And since then, we have grown quite a lot. We have more than 30 partners, institutions, 500 collaborators. And the different collaborators include both national laboratories, academia, and the industry, and both in the United States and internationally. You can see here is our latest group photo from the annual meeting that was just, I guess, a month ago. And in the field of quantum information science, which is the combination of quantum information, of quantum mechanics and information science, there are many fields inside, such as quantum sensing and metrology, cryptography, computing, simulation, and communication. And we think that in the center we can contribute to some of these areas by leveraging the unique expertise that the center has, such as a deep knowledge in superconducting materials and RF cavities, in cryogenics, in electronics and microwave control, and precision timing. And before we go into the physics and sensing part, let me give you a quick overview of what we call the science and technology innovation chain. So for the materials and devices part of the center, we start from the materials understanding to develop a full understanding of the sources of decoherence through a systematic and fundamental science approach. And then with the goal of demonstrating devices that are systematically and consistently with higher performance, higher coherence, by testing this at the different SQMS partners, institutions. And then we want to be able to preserve this high performance when integrating the devices into more complex systems. And with the ultimate goal of deploying quantum platforms based on innovative architectures that still maintain improved performance. And then we want to demonstrate quantum computing and also sensing advantage for particle physics and other scientific applications. And so in the technology trust of the center, what we want to do is to start from a basic understanding in order to achieve a coherence improvement that can be applied both in the 2D and 3D high coherence architecture for the quantum computer. And this is based on the core strengths of the different partners. So at Fermilab, one of the pillars is the expertise on the world's highest quality factor superconducting RF cavities. And this is part of the what we call the 3D structure, where we can achieve second level coherence, which corresponds to quality factors of 10 to the 10 or above. And obviously, in order to achieve this, we had to develop a deep structural and superconductivity knowledge of niobium, which is also a key part of the 2D qubits. And then we also have expertise in microwave, cryogenics, mechanical engineering, and large-scale integration experience, since our background comes from the accelerator field. And other parts of the center instead bring to the table a deep 2D and 2D superconducting qubit and quantum processor expertise, and more basic materials and superconducting expertise. And all of this is applied to the materials and devices to advance the research on qubits, both 2D and 3D. But on my side of the center, we want to actually use quantum information science to advance fundamental physics. So, for example, to study questions such as foundational quantum mechanics, what is the physics beyond the standard model, dark matter, and, for example, simulation of quantum theory. So, in the science trust, the type of questions that keep us up are, for example, as listed here, for example, what is the non-equilibrium dynamics of highly entangled systems, or what is dark matter? Can we detect high-frequency gravitational waves? And so the first type of questions go under quantum simulation computation, and the second under quantum sensing. Obviously, all of these are long-term endeavors. We don't think we can achieve them tomorrow, but we want to try to enable breakthroughs in these topics. And so the people that work in physics and sensing, you can see some of the faces here. In general, thanks to the center, we have both theorists and experimentalists that work very closely together, and we have expertise in different fields such as high energy physics, materials such as sensing, QAS, and RF engineering that once again work very closely together, and in just the past 2-3 years have been able already to achieve some incredible results. And so going into Mago 1.0, I think you already heard from Christian before me, so I will not go too much in depth on the background of this cavity. But the idea is that we can use high QSRF cavities to search for high frequency gravitational waves. And this was an effort that started at the end of the 90s by Einstein and CERN. Through the microwave apparatus for gravitational wave observation, they had successful proof of principle and prototype experiments, and then they designed and fabricated 2 cavities made of niobium. The first one here with fixed coupling, and the second one down here with variable coupling. And the second cavity was never tested. It lied on a shelf for the past 15 years at INFN Genova. And now we are reviving this effort in collaboration between Fermi, Lab INFN, DAISY, and the University of Hamburg to revive this cavity and test it for the first time and understand what can be done with the existing cavity and what can be improved for a future design. So the cavity, I think as of today, is traveling from DAISY to Fermilab. And at Fermilab, we are very excited to finally receive the cavity. For the moment, we have been working on some preparatory studies and issues to be able to then test the cavity when it will arrive. So obviously, similar to DAISY, we also conducted RF simulations and also mechanical simulations with both the ideal and the real geometry and thickness that with the data that DAISY measured and kindly shared. And we had to optimize the frame for the cavity in order to relieve the stress from this thin coupling cell, because the cavity will be tested in liquid helium at cryogenic temperature, either 2 Kelvin or even lower. We can achieve about 1.4 Kelvin. So we need to be able, obviously, the cavity needs to withstand that pressure while under vacuum. We also had to understand how to elastically tune the cavity at room temperature in order to bring it back to an acceptable state, which is not necessarily the ideal geometry, but at least an acceptable starting point, because right now the cavity is pretty bent, so there are some concerns with leaving the cavity as it is. We don't currently have plans of cold tuning. Regarding chemical processing, we had to evaluate if we could do obviously BCP or EP, and if we wanted to conduct bulk or only light chemistry, and also understand if vertical or horizontal setup would be more appropriate for this case, since this central cell has very thin walls and it's an area of high removal. And one more thing to consider was the HPR, because this cavity has a pretty narrow, let's call it beam tube. And then for the one more concern was the heat treatment as well, because the flanges of the cavity are stainless steel, and we didn't know initially the brazing material. Then talking with Sergio Caltroni, he kindly retrieved information from 20 years ago that was able to shed some light on the previous treatment and brazing material of the cavity, which gave us some confidence that we will be able to do the heat treatment if necessary. And then at the same time, we are also conducting on the theoretical side some simulations to simulate the coupled oscillators subject to mechanical vibrations, both as microphonics, so ambient vibrations in the liquid helium environment, but also vibration induced by the gravitational waves, in order to derive the expected growth rate of the signal mode when the pump mode is excited, and understand how the non-idealism of the cavity will contribute to this parametric energy transfer. And we think that the combination of the experimental activities of MAGO 1.0 and these simulations will inform the design for the next generation cavity. So looking forward on MAGO 2.0, we are probably leaning toward a broadband non-resonance search, meaning that for the MAGO 1.0 cavity, so the T modes that we will be using are at a frequency of 2.1 gigahertz. The splitting between the two is about 10 kilohertz. And if we were to want to conduct a resonance search on a broader range, we would need to obviously tune our cavity so that the splitting between the modes matches the frequency of the gravitational waves to which we are more sensitive to, and it also needs to be close to a mechanical resonance, an appropriate mechanical resonance. So it obviously would require multiple cavities, and it's pretty complicated to run a resonance search on a wide range of frequency. So one more option that was one more option that was brought forward in the MAGO 2.0 paper that is referenced here is the possibility to a broadband no resonance search, where we are not tuning on the frequency splitting. So that is something that we are evaluating, and obviously we want to keep developing the simulation side of the work in order to understand all the details of, for example, the imperfection in the cavity shape, the type of microphonics background that we can have in the liquid helium environment, how it will affect the search sensitivity. And we currently also have a small effort of collaboration between United States and Japan with the University of Tokyo and KK. And we are based for SRF-based gravitational wave searches. We are currently focusing on the design phase of a new cavity and tuning system, and obviously the lessons learned from Mago 1.0 will be crucial on this. And I think Christian also already mentioned this in his talk, but for this type of searches, it's really crucial to have a custom cryostat and suspension system that allow to run in a very low noise environment. So that is something that we haven't yet started to look into, but it will probably be necessary. Okay, so obviously you already know, but for gravitational wave searches, it's particularly important to have a series of coordinated and synchronized experiments at different locations. So we are hoping that Mago 2.0 may become a global experiment involving many laboratories. And so I thought I would give you a short outlook on our facilities at Fermilab and other experiments that we are conducting. So this is our liquid helium test and facility. This was built for Accelerator purposes. So these are what you see here in the ground are 3 different pits where we are able to test cavities for Accelerator and now also for physics and sensing. This is what the open pit looks like. And for example, here we are installing into the dewar is what we call the vertical insert. You can see a cavity installed here. And as you will see in a couple of slides, this is the dark SRF setup. The way it works is that this whole vertical insert will be inserted into the dewar. And the cavity will be cooled to 2 Kelvin through liquid helium. So they will be submerged in helium using a couple of thousands of liters. And then we have this orange cement block, which is used to shield radiation that may be produced when we go to high gradient and we have phenomena like, for example, field emission. And we also have a few diagnostics that we can use around the cavities to understand, for example, to detect obviously the temperature of the cavity, the magnetic flux, and similar parameters that can be important during the test. And this instead are the newer SQMS laboratories. Here on the left is what we call QCL3, the quantum garage, and on the right is our first dilution refrigerator. These are all dry dilution refrigerators where we can conduct tests to a few or dozens of millikelvins. And for example, here on the right, you can see in the fridge, there are 2 cavities assembled, a bullet with resonators or qubits, and this is often what the fridges will look like for our experiments. Okay, then going into the other experiments, so the quantum sensing area of the center works on multiple topics, not only gravitational waves, which is actually an effort that we started pretty recently, but we have a lot of experiments on the dark sector, both as dark matter and just new particles, and also precision measurements. And so for dark matter, we started with a dark photon dark matter search at fixed frequency, so a sort of proof of principle to demonstrate that high Q cavities can be useful in this field to achieve very deep sensitivity. And so we demonstrated the reach for dark photon dark matter at fixed frequency. And our next step for this effort will be to use a new cavity that we designed and built, which is tunable from 4 to 7 gigahertz, because in this field, we, once again, it's important to have a tunable cavity so that we can cover relevant, a wide area of the dark photon mass. And so this is the projected sensitivity with this new tunable cavity that you can see here. Both the existing limit and the next search are conducted in the dilution refrigerator. And the next step will be to combine these type of searches with photon counting so that we can go even deeper in sensitivity. What I mentioned before as what we call the 3D architecture is when we combine transmon with a 3D cavity. And this is something that we haven't yet deployed for quantum sensing, but we count on doing very soon in order to be able to count photons in the cavity non-destructively. And being able to achieve lower lower noise, and so being able to dig deeper into the parameter space of the dark matter searches. One more effort for action searches, you may be familiar with this type of particles, but in order to be able to detect them, we need to apply an external magnetic field. So niobium is not the ideal material for this type of experiment. So one possibility is to use niobium-13. And you can see here the performance of a cavity that we designed and built. This is a bulk niobium cavity with a niobium-13 film with an optimized shape for this type of search, and Sampleton was able to demonstrate a quality factor of 5 × 10⁵ Tesla at 4.2 Kelvin, which is an order of magnitude above the, for example, the copper quality factor. So this could be a promising road, but also there are different approaches, like, for example, superconducting materials, but high temperature superconductor that seem to be a very valid option that have already given higher results in terms of quality factor. And as for dark SRF, the experiment that I had mentioned before, this is a light shining through the wall search with SRF cavities, obviously looking for the dark photon, this time not as a dark matter experiment, but as a light shining through the wall. So where this is our emitter cavity that is excited to high field, and with the possibility of producing dark photons that would be able to escape the cavity walls and could be detected in this second cavity. In this case, it's crucial that the two cavities are tuned to the same frequency. And what you see around these emitter cavities, indeed, a tuner system so that we can control the resonant frequency and match it to the receiver. We have conducted this search in liquid helium and published recently the results. This was the type of limit that we derived, so we were able to exclude the area shaded in blue. Obviously, we didn't find any dark photon, but we, through this pathfinder run, we were able to exclude new parameter space, so that was a very successful result. And we are looking for the next phase to conduct the experiments in a dilution refrigerator this time, so that we can go once again deeper in sensitivity. And in order to do so, we had to change the setup quite a lot, because we need to change frequency so that the cavities are smaller and can fit in the dilution refrigerator. We had to change the tuning system because the one from the liquid helium is too bulky and too dissipative. And we are now wrapping up all of these changes. And so far we have been doing troubleshooting in the liquid helium. So we hope that soon we will be able to move into the dehuser refrigerator. I think, okay, one last thing very quickly. We are also working on a heterodyne and dark matter search. This is based on this Asher-Berlin paper. The idea here is that we only use one SRF cavities, no magnetic field is applied. We use multiple resonance modes of the cavity in order to be able to detect the axion dark matter in the cavity. And in this case, the mass of the axion would correspond to the splitting between the two resonance modes used in the search, which enables us to search for very small masses without using extremely large cavities. And this is what the real cavity will look like. Also in this case, we will have a tuner system around the cavity, and the search will be done in liquid helium. The design is completed, and they are currently fabricating the cavity, which should arrive either at the end of this year or at the beginning of the next year. And we are really looking forward to start testing this cavity. And I think that's all. So thank you for your attention, and let me know if you have any questions.